Hi friends, today let us see how we can utilize the frequency domain characteristics of a given window function in designing an FIR filter. In this type of problem, the window functions are not specified. We need to actually analyze from the given characteristics in the problem which type of window need to be used. For example, let us see this problem. It says that design a normalized linear phase FIR filter having a phase delay of tau is equal to 4 and at least 40 dB attenuation in sideband, also magnitude and frequency response of the filter. Now we will analyze the problem till this part because it's a design problem till this part. After that, also obtain the magnitude and frequency response is the analysis problem which we have obtained or done in chapter number 1. So let us understand first how to use these 3 lines and design an FIR filter. Now what are given? Given is a linear phase FIR filter. Phase delay should be or must be 4 and stop band attenuation must be at least 40 dB. That is what the given scenario is. So if I write the given, then I want tau which is same as that what is alpha, which is 4, stop band attenuation which we write as AS, which is 40 dB, and the demand to write to design a normalized FIR filter. Now how to go about this problem? First of all, let us understand and one more thing which is not been specified in this. We will assume that we are using a low pass filter. So we will be using an LPF, or we will be designing a low pass filter only. So with this given data, let us start designing the filter. Step 1 would be, first we need to obtain our HD of e raised to j omega. So let us first obtain HD of e raised to j omega for the given filter. Now as we have considered a low pass filter, we know that HD of e raised to j omega will be equal to 1. In the bracket it will be e raised to minus j alpha omega. Now alpha over here is 4. For minus omega c less than equal to omega to omega c, that is from negative cutoff frequency to positive cutoff frequency, and is equal to 0 otherwise. So I need to actually find what is my cutoff frequency is. So let us understand. So how will I get the information from the problem that I wanted to what would be my cutoff frequency? So in the problem it has been designed that design a normalized low pass filter. Whenever they say that you have to design a normalized low pass filter, that time the word itself means that your cutoff frequency is 1 radians and your modulus of HD of e raised to j omega should be equal to 1. That means the amplitude height should be equal to 1 and the cutoff frequency should be 1 radians. That is what it means that we need to use a normalized filter. So with this statement, we can go ahead and we can write HD of e raised to j omega will be equal to 1 e raised to minus j 4 omega from minus 1 less than equal to omega less than equal to 1, because it has been specified that we have to design for a normalized filter and it is 0 otherwise. Okay, now let us so we got the cutoff frequency. Now let us go for step 2 and apply inverse DTFT, which will give me h of, let's say hd of n, which is equal to 1 upon 2 pi integral from minus pi to pi hd of e raised to j omega n d omega. Okay, so when I substitute this, I'll get 1 upon 2 pi, okay, from minus 1 to 1 and everywhere else it is 0. hd of e raised to j omega is e raised to minus j 4 omega e raised to j omega n d omega. That will be 1 upon 2 pi minus 1 to 1. Let's say this I can reduce it to e raised to j n minus 4 omega d omega, and then that will give me as 1 upon 2 pi, this will be e raised to j n minus 4 omega divided by j n minus 4 from minus 1 to 1. Let us substitute the values for the given problem. When we substitute, we get hd of n equals to 1 upon 2 pi. First value is e raised to j n minus 4 minus e raised to minus j n minus 4. So when you put minus 1, this degree goes to minus 1 and here it is plus 1, divided by n minus 4 into j. So I'll use this 2 and j, then it becomes 1 upon pi n minus 4 we will utilize here, and 2j with this will give me sine n minus 4. Okay, that is my hd of n. So once we have done with hd of n, now the next step, this will be infinite, right? Because my n don't have any limits onto it. Then we have to apply step 3, which states that I need to obtain a finite h of n, which we say that h dash of n, which is nothing but hd of n into w of n. So with this given, so now I wanted to know what is my w of n. Let us go back to our problem. Now in the problem, we don't find anywhere that which window to be used, but we will focus on this point to design or to select a window, that is at least 40 dB of attenuation in the sideband is required. The number is given as 40 dB. Let's go back to our characteristics. Now the characteristics that we have for the window, this is the minimum stop band attenuation, this column. I want minimum to be minus 40. If I give minus 44, it will also be better. If I give minus 53, will be more better. And if I give 74, then it's also a very good filter. Okay, so out of the 5, the choice is of the designer whether I should go with Hanning or with Hamming or with Blackman, because all of these 3 satisfies the given criteria. In our case, we will be only considering the next highest one, that is the 44 dB. So with the 44 dB, I will be going with the Hanning window rather than using either Hamming or Blackman. So this is how we need to identify which window to be used. So since the minimum stop band attenuation is 40 dB, we will select which one? The Hanning window, because Hanning gives me 44 dB of attenuation. Okay, so this is how we normally select the attenuation of a filter. Now with this, we are ready to go ahead and write the window function. So let us write the window function. The window function states that we are going to use an Hamming window. So now our step 3 will be h dash of n to be equal to hd of n into w of n, and our w of n, which is Hanning, which is 0.5 minus 0.5 cos of 2 pi n by m minus 1 for 0 less than equal to n less than equal to m minus 1, which will be 0.5 minus 0.5 cosine 2 pi m by m is we don't know m, but we know alpha. So for here I'll do the calculations over here. We know, because we know alpha is equal to 4 and alpha is equal to m minus 1 by 2. So if we write 4 equals to m minus 1 by 2, so it will be 4 to the 8, and if I take that 1 on that side, 1 plus, so m goes as 9. So the length of the filter required is 9, that is 0 to 8. So I can write here m minus 1 as 8 and 0 less than equal to n less than equal to 8 again. Okay, now how will we go about? I will write the values of n, then we will write the value of h d of n, then we will write the values of w of n, which is a window function, and finally I'm going to write the values of h dash of n, which is nothing but product of these two. The values of n will go from 0, 1, 2, 3, 4, 5, 6, 7 and 8, because there are 9 total elements. Which element will create problem? The element of alpha will create problem, that is n is equal to 4, where the function will go as infinity. So we need to solve this separately. Okay, rest everything can be solved easily. So the first value of when you put n is equal to 0, in hd of n will be minus 0.06. For 1 it will be 0.01497. For 2 it will be 0.1447. For 3 it will be 0.2678. For 4 it will come as 0.3183. Okay, because we are dealing with a linear phase filter, this value is going to replicate over here, so it will be 0.2671. then this value will come again, so it will be 0.1447. then you will get this value back, which will be 0.01497, and finally you will get minus 0.06, which is this value. Okay, so you are going to get this because we are dealing with a linear phase FIR filter. Okay, similar way the window function gives answer as 0, 0.1464, then 0.5, then 0.8535, then 1, then 0.8535, then 0.5, then 0.1464, and then it is 0. Okay, now when you multiply this number by 0 will be 0. Here you will get 2.1916 into 10 raised to minus 3. Then we have taken 0.0737235. Then we have 0.2285. Then we have 0.3183. Then we have again 0.2285. Here it will be 0.07235, and lastly here you will get 2.1916 into 10 raised to minus 3, and lastly will be 0. So this is the final answer of the design problem. So whenever you write the final answer, don't write in this form, you just write this in the roster form. So how to write this in the roster form or in the set builder form is h dash of n will be equal to, the roster form starts with a brace bracket, 0 comma 2.1916 into 10 raised to minus 3, comma 0.07235, comma 0.2285, comma 0.3183, then again 0.2285, 0.07235, comma 2.1916 into 10 raised to minus 3, comma 0. So this is what the final answer will look like when they ask you to design an FIR filter. Thank you.